Okay, 2.1, example 5, part B. The instructions were to find the domain, give the answer in set or interval notation, and of course we're always going to be showing our analysis. So we want to show our steps essentially. First of all, the function's name is m and the independent variable is t. So when we find our domain, we're finding the values of t that work. We do have a 6t in the numerator. Is that affecting the domain at all? No. So what do we do with the 6t? Oh, we don't forget it. We just, hi 6t. Hi. That's how 6t talks. It's not in the denominator, so it's not going to affect the division by 0, and there's no radical associated with it, right? Either overt or covert. There's no fractional exponent. So it's just in the numerator. But in the denominator, whoa, we got to be careful now, right? Because we have a square root with a variable beneath it, and it's in the denominator, there's a variable, so we might have division by 0. So we'll treat the two things separately. What should we do first, the radical or the denominator? The radical, okay? So 4 minus 7t shall be what? Greater than or equal to 0. And again, this is the one with the negative variable, so if you're going to leave it on the left side, where we'd like to have it ending up, make sure that you do everything else correctly. It becomes a what kind of 4 on the right? Negative. And then when I divide through by negative 7, I do what with the inequality? Flip it, less than or equal to, and then I get positive 4/7. Quickly checking, to the left of 4/7, like 0, it should work. Plug it into the radical, and you get square root of 4, that's good. Something greater than 4/7 that shouldn't work, like 1. 4 minus 7 is negative 3. Under a radical, that's no good. So this is probably correct, more than likely. Now, we need to look at the denominator. So what do? We take part of the denominator or the whole thing? The whole thing. The square root of 4 minus 7t, and we say that it shall not be equal to 0. So again, that's the analysis. Showing the inequality, that's going to be 1. This will be 2. Checks if we're checking this. 3 would be that. And now, how would I solve this radical equation? I would square both sides. We have our radical isolated. If we square both sides, we get 4 minus 7t shall not be 0 squared, which is 0. And so if we solve, we get negative 7t shall not be negative 4. T shall not be 4/7. And if you plug that back in, it's always a good thing to do to try plugging that back in. And you'll see that you get 7 times 4/7 is 4. 4 minus 4, bless you. 4 minus 4 is 0. The square root of 0 is 0. And that would be then our entire denominator, which is no good. So remember that the inefficient way then to combine your results, the non-thinking way, would just be to say the domain of function m would be the set of all t such that t is less than or equal to 4/7, comma, oh yeah, and by the way, don't use 4/7. Right? Kind of silly. I love peas and carrots, but I hate carrots. But you just said that you love peas and carrots. Yes. That is exactly what we're going to do, right? If you're trying to communicate to someone that's like peas, you don't say I like peas and carrots and I hate carrots. You just say I like peas, right? That's how we're going to do it. We are going to combine our results in a very efficient way. Instead of saying less than or equal to 4/7 and giving everyone a tease that we can use 4/7, just to take it away, we'll just say in the beginning, hey, t has to be strictly less than 4/7. That's how you should do it, okay? If you did it like this on a free response, would you be wrong? No, you'd be silly, but you'd be correct. But on a multiple choice question, that would not be the answer choice. So think before you give your final answer. Now, in the beginning, if you would have known that, you could have said, oh, normally I can have a 0 under a radical, so I say greater than or equal to 0. But in this case, that would result in a 0 in the denominator, so in this case, my radicand has to be strictly greater than 0. If you can do that, that's fine. Okay? You could have just said 4 minus 7t is strictly greater than 0. Whoa, that doesn't look like a good 0. It fell. There we go. And that will give you essentially both checks for the first one and the second one. But if you're not sure how to do that, put it as 2 separate steps, 2 separate analyses, and then combine your results efficiently. Okay, any questions on that one? All right. Bless you. It could be that you like peas and carrots, but you hate carrots. Like the peas kind of offset the nastiness of the carrots enough that you like them together, but when you eat them by themselves, they're nasty. So that would be a grammatical lesson on the Oxford or the serial comma, which we're not going to get into today. Okay? All right, very good. We have a function. What's its name? Yeah, it doesn't really have a function designation here, so you can just call it y. We have a square root, yes? So, and there's a variable underneath it, so that's going to be an issue. And we have a denominator with a variable, so it can't be 0. So step 1, we take the entire radicand, and we say that it has to be what? Greater than or equal to 0. And then we solve. How do I solve for x? Multiply both sides by -1. 0 times -1 is 0. But what do I do with the inequality? I flip it. Okay. Divided by what? Oh, that's fine. Either way. Yeah. With -1, you can multiply or divide, and you get rid of it. Yeah. If that was like a -5, you couldn't multiply both sides by -5. So, yeah, either way. Good point. But let's check, right? We're saying that x has to be strictly 0 or negative to work. Well, since there's a negative in front of the x, some people look at that and say, oh, that never works because you can't have a negative under a radical. Well, you're right. If it's a square root, you're right. But x is a variable, so as long as x starts off being negative, like plug in a -5 for x. Everyone have it? What am I going to immediately do to that -5? I'm going to multiply it by -1. Or you can think of that as the opposite of x. That's another way to read that. The opposite of -5 is +5. And that works, okay? So that's the radicands, demands of the radicands. And then we take the entire denominator, x squared plus 5, and we say that it cannot be 0. Now, if you're thinking, you might already kind of know something about that. But if you're not thinking, you're just kind of forging ahead. Let's keep doing that. Then you're saying x squared cannot equal -5. And if you're thinking, you might already be able to say something about that. But if you're not thinking, you forge ahead, and you say that x cannot equal plus or minus the square root of -5. And you're like, oh, the square root of -5. What type of number is that? That's an imaginary number. Strictly imaginary. It's a complex number, but it's strictly imaginary. And so what we're saying is that only imaginary numbers make the denominator 0. We're dealing with what types of numbers by default? Real numbers. So if only imaginaries give us division by 0, then I guess all the real ones work. Okay? And you could have spotted that up here. Because think about it. Take any real number in the whole wide world, x, square it. Are you going to get a negative number? No, you're going to get 0 at the least or a positive number. So you could have spotted that here. Similarly, x squared plus 5. If you think of that graphically, ooh, that's good. What does the plus 5 do to our graph of x squared? It moves it up 5, and now it looks like that. Is that thing ever equal to 0, 0 being way down here? No. So you could have spotted that in the beginning. So even though there was a variable in the denominator, no values of x made it 0, right? So there were no restrictions. So the only restrictions we had were from the radicand, okay? It's like an arbitration between the radicand and the denominator, and the radicand's like, I have to be less than or equal to 0. And the denominator says, that's cool with me. Has no demands of his own. So it's the domain of, and if you want, you could say sub y, but if it's not a function, you don't have to put a subscript. And it'll be the set of all x such that x is strictly less than or equal to 0. So we still considered both, denominator, radicand, but denominator works for every value of x. So I guess the moral of this story here, this little tiny boring story, it's not really a story, is that just because there's a variable in the denominator doesn't mean there's going to be any restrictions because of it for the domain. All right, questions on that? I know I'm boring you. I'll try and speed it up here. Letter D. 15x minus 3. Does that affect the domain? No. Anything in the numerator, unless there's a negative exponent, is not going to ever give you division by 0. So the only time the numerator is going to be of interest to us is if it is inside a square root or a fourth root function. Otherwise, it's good, right? Hello, 15x minus 3. Good to see you again. We look to the bottom, we have a square root, and there's a variable underneath it, and there's a variable in the denominator. So once again, we have both things to check for. So step 1, 3 plus 5x squared has to be greater than or equal to 0. That's 5x squared plus 3 has to be greater than or equal to 0. Oh my, oh my, oh my. What type of inequality did I just set up? Quadratic. It's x squared. Can we solve those algebraically? No, we cannot. So we solve them graphically. Now, 5x squared plus 3 is in standard transformation form already, believe it or not. The 5 is just going to be a vertical stretch by a factor of 5, and the plus 3 moves it up 3. So it has a vertex here at 3, and can y'all tell that my graph there is 5 times steeper than the normal parabola? Everyone say yes. Good. That's how I'm going to be grading yours. We're trying to figure out for what x values is that thing greater than 0 or equal to 0. And remember, that's y equals 0. This is y equals the parabola and y equals 0. Here's y equals 0. For what value of x is that graph above or on the x-axis? All of them, right? All of them. So the denominator, the radicand under the radical will always be a positive number. So we're not going to ever have any negatives under the radical. So we've cleared the radical hurdle for all real numbers, yeah? Well, the next hurdle we have to clear is the division by 0. So we take the entire denominator, 3 plus 5x squared, say it can't be 0. We now have a radical equation. We solve it by squaring both sides. 3 plus 5x squared then shall not be 0 squared, which is 0. Well, if you look at the graph, right, for what values of x now is this graph not equal to 0? 0 is down here. All of them, right? It's never 0. It's 3 at the very least. If you didn't see it there, you could keep going. 5x squared cannot equal negative 3. X squared cannot equal negative 3 halves. X cannot equal then plus or minus the square root of negative 3 halves. And you're like, oh, it only has imaginary restrictions. 3/5. That was so close, but I still lost the point. Thank you. So it only has imaginary restrictions. So I have cleared the division by 0 hurdle. I've already cleared the radical hurdle with no restrictions. If it passes both hurdles, if it passes both tests with flying colors and there's no restrictions, guess what the domain is? All real numbers. So you could say D or D sub y. It's all real numbers. So another boring little short story here, the moral of which is just because there's a denominator with a variable doesn't mean there's going to be restrictions, and just because there's a variable under a square root doesn't mean there's going to be restrictions. You check each function on an individual basis. Okay? Individually, combine your results, and you've got it. Nothing to it. The 15x minus 3 later on will affect the function, but not the domain. Okay, the next 3 are all very, very similar. The only difference is their denominator. We'll do E together, and then I'm going to let you do F and G, give you about a minute for each of them, because it's going to be very similar. And I'll pass back some papers while y'all are doing that, and kind of check on how you're doing it. We do have function notation again, so we're going to have to use D sub F. We have a square root in the numerator and variables in the denominator. So 5x minus 3 better be greater than or equal to 0. Radicand greater than or equal to 0. X has to be greater than or equal to 3/5. Okay, and if you check something bigger than 3/5 like 1, it works. Less than 3/5 like 0, it doesn't work like we would expect, so that's correct. Now that's going to be the numerator in the other 2 problems as well, as you'll see. So that analysis for the radicand will be the same in F and G. But what's different in each of the subsequent 2 after this are the denominator, which will set up x squared plus 2x minus 3 cannot be 0. And then we try to do what? Factor? Yeah. And hopefully it'll factor. Fingers crossed. Factors of negative 3 that add to positive 2. Positive 3, negative 1. Cannot equal 0. Make sure you're bringing the can equal 0 down. And then we get x cannot equal -3, nor can it equal +1. So now we have the demand of the denominator, and we combine the results, but we only need to, again, exclude those individual values from the denominator that happen to be greater than 3/5. Which of those two, if any, is greater than 3/5? 1. So the 3 is already excluded. So we will write our domain then, d sub f. It's the set of all x, such that x is greater than or equal to 3/5. Oh yeah, and by the way, don't use 1. If you write that as an interval, once again, you got to start at 3/5 with a beefy bracket, cruise all the way to your first restriction, which is going to be at 1, step over it, go to your next restriction, which is never. Again, that'll kind of prevent you from trying to get -3 excluded because it's not even in your interval. Okay, so the next two problems I want you to do on your own. Very, very similar. Again, the numerator is the same. What's different are the values you're restricting in the denominator. See what you get, and then I'll be passing back some of y'all's papers while y'all do that. This is the part on the video, if you're watching it at home, that you try these on your own. Bless you. Haley. Yeah, here you go. That was yours, Tyler. CC. All right. So everyone should have back everything so far from the whole year. Those are all good things to revisit, to kind of look at in preparation for tomorrow's exam. All right. So on on the next two, the demand of the demand of the radicand was still greater than or equal to 3/5, right? What's different is the way it's factored. So on the bottom down here, I'll put the denominator for part F and say it can't be 0. That factors into x plus 1, x plus 3. And so we get x can't be -1 nor -3, right? But we only have to exclude them if they're greater than 3/5. Are either one of those greater than 3/5? No. So in this case, the domain of our function g is just the set of all x such that x is greater than or equal to 3/5. No value bigger than or equal to 3/5 made the denominator 0. So you don't need to exclude them again. The other one here, if we set this, again, equal to 0, which is better to do before the factorization, that factors now into x minus 1, x minus 3, which means now x can't be positive 1 or positive 3. Both of which now are greater than 3/5, and so we would need to exclude those. So the domain of function r is the set of all x, such that x is greater than or equal to 3/5. Oh yeah, and by the way, comma, don't use 1 or 3. Okay, so those three problems together kind of give you an idea of what happens when you have domain restrictions of both varieties. You only have to exclude the singularities, the ones that give you division by 0, if they are not already excluded by the radicand. All right, questions on those? Yes?
I made two really small mistakes, and I was wondering if you
If it's a free response question, here's what I'm looking for. When you set it equal to 0, you're going to get 1 point. Then you find the roots. That would be the second point, both of them. Now, you probably lost the second check, I'm guessing?
No, like they're like really small.
Well,
Okay, for D of R, I put a different variable, and I didn't put them in order when
okay, so you put like D sub F?
Yes, sir.
You would not lose points for that. Good question. Yeah, it's better that you put sub R, but if you put a different function's name, I'm not going to be that big of a deal or make a big fuss about it. Similarly, up here, remember how we had this function that had t's in it? Where was it? Way up here? Further down? We had there it is. If you would have said the set of all x such that x is less than or 4/7, I wouldn't have taken off either, even though they're technically t's. That's all stuff you'll get used to.
What if it's free response? I know last time, whenever we had to plug in for your the functions, we put a bunch of different ones. I actually plugged in the wrong function instead of like x vector and h vector.
Oh, if you plug into the wrong function, that would lose a point. But if you call that function a different name, then that's, yeah. Because then you're working a different problem. There will be a time when I'll take off if you put R instead of, or F instead of R. What was your other mistake, Haley?
It was not putting x cannot be equal to 1 or 3, but I put 3 or 1.
You put x cannot equal 3 or 1. I'm not going to get too big in a fuss about that either. So you would get full credit for that. Yeah. Okay. All right. Now they're going to get a little bit more interesting. Remember, there's two hurdles we have to clear, right? We don't want to take square roots, fourth roots, eventh roots of negative numbers, and we don't want to divide by 0. We have 3 terms in this problem now. It's a different example, but same exact instructions. If you have more than one term, each term has to clear both hurdles. Okay, so let's do that. Negative 6x squared. Any chance of dividing by 0 there? No. Does it have a square root, fourth root, sixth root anywhere? No, there's no fractional exponents. There's no negative exponents. There's no overt radicals, no denominator other than 1. So the first term passes both hurdles. Good. On to the next one. Hey, we have a square root, right? Careful. Radical alert. What's under the square root? 3 or 3x? 3. If you look carefully, it's only the 3 that's under the radical. If you're writing that on your paper, you need to make sure that the radical only extends over what it's supposed to. Is there any risk of 3 ever becoming a negative number? It's a constant, right? So even though there's a radical, there's no variable underneath it. It passes both hurdles. Okay, so it's good. The last term has a denominator, of course, right? So we're trying to avoid division by 0. But what do we have in the denominator? 3. Is 3 ever going to be 0? Even when you're not looking? No. It's always a 3. So again, it passes both hurdles. And so if every term does that, the domain is all real numbers, which you can write like that. So just because there's a radical, just because of the denominator, doesn't mean there's going to be restrictions. First of all, we have to have variables under square roots, fourth roots, and variables in the denominator. And even then, we saw up above, there still might not be restrictions. All right, g of x equals 4 to the x minus 5. 4 to the x. That's different from x to the fourth, right? Remember that if we have negative exponents, those are denominators in disguise. And if we have fractional exponents, those are radicals in disguise. But if I make x a negative number, is that going to put a 0 in the denominator? No. When you have a novel situation, let's just try some things out. Let's try x equals negative 1. We'll get g of negative 1 equals 4 to the negative first minus 5. We have a negative exponent now, which means we have a fraction in disguise. But what's another way to write 4 to the negative first? 1 over 4 to the positive first. Did we get a 0 in the denominator? No. In fact, anytime x is a negative exponent, it's not going to cause a 0 in the denominator. It's going to cause a 4 in the denominator. And is that okay? Heck yeah. All right, now what about the fractional exponent? Let's try x equals 1/2. That's going to be a square root in disguise, right? So g of 1/2 is 4 to the 1/2 minus 5. We're trying to avoid what types of numbers under square roots? Negatives. 4 to the 1/2 is the same as the square root of 4. Is that a negative under a radical? No. So any fractional exponent here is not going to cause a 0 or a negative under a radical. It's going to cause a positive 4 under a radical, which is okay. The minus 5 clears both hurdles easily, right? So both terms clear both hurdles, so guess what the domain is? All real numbers. This 4 to the x belongs to a family of functions called exponentials. Okay? Like e to the x, 2 to the x, 4 to the x. And we'll study those later in the year. And you'll find later on that the domain of all exponential functions of this form, it's always going to be all real numbers. Their close cousins, logs, though, not so lucky. Logs have domain restrictions. But we're not going to be dealing with logs yet. All right? Looking at this one here, 2 square root of 3 in the bottom. Good, right? Nothing to it? Nothing to it. Cube root of variable. Do we need to worry about negatives under a cube root? No. Guess what the domain is? All real numbers. So d sub h is the set of all x or t? In this case, it's t, such that t is an element of the real numbers. Do we have to do that? Nah. If it's all real numbers, you can use the symbol. Okay, there you go. Our test will be, I guess, through example 6. Yeah, that's nice. Because the more fun ones were on example 7. But I'm not going to test you over that. I'll be here in the morning at 7:15 if you have any last-minute questions. Until then, have a great day. See you later.